So, in the last lecture we had looked at Fick's first law, and just to restate it again, the Fick's first law of diffusion in one dimension can be written as the flux of atoms in a concentration gradient is given by J equals minus D dC by dx, where dC by dx is the concentration gradient, D is the diffusion coefficient, J is the flux of atoms. So, for instance, if I had a concentration in a bar of solute atoms in this fashion, then the slope of this line is dC by dx, and this will indicate, this particular relationship of Fick's first law will indicate that flux of solute atoms would take place from higher concentration to lower concentration. We had seen this relationship in another context in the lectures on diffusional growth. So, just to recall, we had this situation where there was a beta precipitate growing in an alpha matrix. So, beta precipitate has a concentration of C beta, concentration far away from the beta into the alpha is C naught, while the equilibrium concentration at the given temperature of alpha is C alpha. So, here inside alpha, beta is growing in this direction, and inside alpha there is a concentration of the solute atoms given by this line. Here we had assumed that this was a linear relationship for simplicity. In this context, there was a flux of solute atoms in this direction, and which we had written as this flux as d times dC by dx. Note that we had not written any negative sign here as it is written in the Fick's first law, because we had simply written that this was the magnitude of the flux, and the flux was clearly from a higher concentration to a lower concentration, and this flux then was related to the velocity of the alpha beta interface that was growing into the alpha. Consider another situation. Suppose I had a thin mild steel sheet of 0.1 weight percent carbon, or let me make it 0.15 weight percent carbon, and let us say I have a decarburizing gas on this side of the mild steel sheet, such that the concentration of carbon on the surface of the sheet is kept at 0.1 weight percent carbon. On this side, on this surface of the sheet, we have a carburizing gas. Such that the surface concentration is fixed at as 1.0 weight percent carbon, and we had a sheet which we started out with 0.15 weight percent carbon. Very clearly, carbon will be depleted on the left hand side because of the smaller concentration of carbon on the left hand side, while on the right hand side the sheet will be enriched with carbon because of the higher surface concentration of 1 weight percent that is fixed on the surface. But eventually, when the steady state is reached, then the concentration in this mild sheet will be given by this straight line. So, here it is 1 weight percent, here it is 0.1 weight percent. So, there is a continuous flux of carbon going in to the sheet from the right hand surface, and there is a continuous flux out. And both of these fluxes at steady state are a constant, and hence the profile or the carbon concentration inside this thin sheet would be given by this linear line. So, if I look at flux at the two surfaces, at surface 1, at surface 2, then at steady state J1 is equal to J2. Now consider another situation where I have a long rod, let us say of mild steel, again of some concentration C0. Now this surface of this rod is exposed to a carburizing gas such that the surface concentration is maintained at Cs. So, if I plot how the carbon concentration varies at different times, so this is my fixed surface concentration. At time t equal to 0, the carbon content in this mild steel sheet is simply C0 everywhere. So, this is the situation, this is the concentration profile at t equal to 0. But we are keeping this at some high temperature so that carbon atoms can diffuse. After some time, the concentration profile would become something like this. So, this is at some time t greater than 0. Now, if I look at the fluxes at different locations in this material. So, if I look at the flux of carbon atoms on this plane A and plane B. So, there is a flux of carbon atoms going into this and the flux going across the two planes A and B. So, if I look at what is the flux at A and what is the flux at B. So, flux at A, Ja is given by, will be related to the slope at point A of the curve. Flux at B would be related to the slope at point B of the curve, and very clearly the slope at A is larger than the slope at B. And if I look at the Fick's first law, it will tell me, because D being constant at both A and B, Ja would be greater than Jb. Very clearly, if I look at this element in this region of the material, there are more carbon atoms entering this region than the number of carbon atoms leaving this region, because there is a higher flux entering the region as compared to the flux of carbon atoms leaving this region. So, there is going to be a build up of carbon atoms as a function of time, and slowly as time increases, these profiles would keep becoming like this with increasing carbon content at various locations. Clearly, there is a time dependence in this diffusion, and we should try to see how we can quantitatively assess this time diffusion and how these concentration profiles will change with increasing time. So, let us consider the situation in this manner. A rod whose area of cross section is A, and if I look at the concentration profile of the solute atoms in this rod, so concentration of solute given by C as a function of distance, this profile is no longer a straight line as we had been taking, but as a curve. And let us consider a small region, a small element in this rod, where we will analyze how the concentration is going to change in this region as a function of time. So, let us consider this as plane 1 and consider this as plane 2, and these two planes are located at, plane 1 is located at x, plane 2 is located at x plus a small increment delta x. So, we are looking at a small element delta x, and the area of cross section of this element is A. So, what is the flux at across the plane 1? So, number of atoms diffusing across plane 1 per unit area per unit time. So, let me write this flux, and this directly comes from Fick's first law, which tells me that the flux should be minus d times the concentration gradient at plane 1 dc by dx. So, therefore, flux at plane 1 would be minus d, the diffusion coefficient, dc by dx, the slope of the concentration profile at plane 1. Similarly, I can analyze what is the flux of solute atoms across plane 2, that is J at x plus delta x. Well, again from Fick's first law, this is minus d dc by dx at plane 2. So, I have dc by dx, there is a slope given by this line, and a tangent here gives me the slope at plane 2 of the concentration profile. Now, let us see the change in concentration in the element delta x in a small interval of time delta t. So, what is the change in concentration of delta x inside this element after time delta t? Suppose the change in concentration is delta c. So this concentration is number of solute atoms or moles of solute atoms per unit volume. So let me multiply this delta c by the volume of this element, and the volume of this element is simply A times delta x. A the area of cross section and delta x is the length of the element. So this is the total change in concentration in time delta t. This should be equal to the rate at which solute atoms are entering this element minus the rate at which the solute atoms are leaving this element from plane 2 multiplied by the area of cross section multiplied by the time elapsed, that is delta t. So, Jx minus Jx plus delta x, this is the net flux per unit area per unit time. So, I multiply it by area and multiply it by time delta t. So, this represents on the right hand side that again the change in concentration after time delta t. So, both of these sides, the left hand side also represents the same thing and the right hand side is also representing the same thing. I can delete this area of cross section and rewrite this equation as delta C upon delta T equals, and let me rewrite this, I interchange these two terms and put a minus sign outside, as Jx plus delta x minus Jx divided by delta x. Now, in the limit of delta t and delta x both becoming infinitesimal, this relationship can simply be written as, in terms of partial derivatives, del c by del t equals minus del jx by del x. This, since J from the Fick's first law is simply minus d del dc by dx, I substitute that and this would become minus del by del x times minus d del c by del x. Since both of them are, we have a sign minus inside and outside, I can just remove the negative signs, everything is positive now. So, this expression that we have is a differential equation which describes the change in concentration as a function of both distance and time, x and t. This relationship is also called as Fick's second law. This is written in one dimension, one can generalize this to 3 dimensions as well. If the diffusion coefficient d is a constant, which in many situations we can assume, then Fick's second law can be written as, essentially we can take the diffusion coefficient out of the differential and it can be written as del c by del t is equal to d del square c by del x square. So, this is Fick's second law in 1 dimensions. So, the solutions to this Fick's second law, we would be able to solve problems like this as to how the concentration profile would vary as a function of time. So, therefore, the next step is, let us explore the solutions to this particular differential equation. So, let us look at solutions to Fick's second law, which del c by del t is equal to d the diffusion coefficient times del square c by del x square. Let us consider a following situation. Suppose I had a thin film of B atoms sandwiched between two rods of long rods of A atoms. So, I have a thin film of B atoms, and out here I have A atoms, and on this side also I have A atoms, forming some crystal structure. And if I look at the concentration profile of B, and clearly at time t equal to 0, this is my concentration profile. However, after some time t1, let us say, this profile would have become something like this, provided the temperature was high enough for appreciable diffusion to take place. So, this could be at time t1. Even after some more larger time, this profile would become broader as B atoms spread on both sides of the thin film. So, here it is T2 greater than T1 greater than 0. So, as time is spreading, B atoms are diffusing. To this kind of a problem, we can apply Fick's second law and solve the differential equation, and the solution to this differential equation is given as, suppose in this thin film I had n atoms of B per unit area, then these concentration profiles as a function of time and distance is given by the following solution of the Fick's second law. So, Cxt, C as a function of x and t, is given by n divided by 2 square root of pi dt times e to power minus x square upon 4 dt. So, this is a solution, this is one of the solutions of the Fick's second law for a situation like this. So, as this is giving me now the concentration profile as a function of both distance and time, you can verify that this is actually indeed the solution to the differential equation is by substituting this solution back into the differential equation, which means that you on the left hand side you will compute by taking the derivative with respect to time, right hand side you will take the second derivative of concentration C with respect to the distance x, and both the left hand side and the right hand side must be equated for verifying the solution. You can also have a situation like this, that I have a long rod and at the end of this rod I coat a thin film of B atoms, and this is all pure A. Then at time t equal to 0, this is my concentration profile of B, and then at later times my profile is going to become something like this. Eventually it should flatten out. So, this is at t equal to 0, this is at some time t greater than 0. The solution to this is very similar to this. Since now the diffusion of B atoms will only take place on one side, where here diffusion of B atoms are taking place on both the sides, this factor of 2 would not be present in the solution, otherwise the solution will remain the same, and hence the solution to this is simply Cxt is equal to n divided by square root pi dt e to power minus x square upon 4 dt. Now, this also suggests a simple way of experimentally estimating the diffusion coefficient d. How can we do that? Well, we can do that in the following manner, that we create a situation like this. We perhaps electroplate B atoms at one end of a rod, then we keep this rod at some temperature T at which some appreciable diffusion can take place for a certain amount of time T. After that, at different distances, we slice the material and measure the concentration of B at different distances x. So, I will have a data of concentration versus distance for a given temperature and a given time. That should follow this relationship. So, how should we do this? Suppose I take natural log of both sides. So, this will give me ln C equals ln n divided by under root pi dt minus x square upon 4 dt. So, taking natural logs on both sides. This suggests that the log of the concentration should linearly vary with the square of the distance. So, if I were to plot that experimental data in the form of log C versus x square, I should get a relationship, I should get a straight line like this. The slope of the line clearly would be minus 1 upon 4 dt. From this slope, I can find out, I can measure or calculate the diffusion coefficient. And in fact, I can then estimate diffusion coefficient for different temperatures as well as at different times. So, I can also study how the diffusion coefficient d varies with temperature. In fact, it will vary with temperature, and we would be discussing this in a subsequent lecture, that how the diffusion coefficient d varies with temperature. And finally, there is one important concept that I can bring in, and which is the concept of self-diffusion coefficient, or simply self-diffusion. So, what is self-diffusion? Well, it is simply, if I have A atoms, I want to find out how fast A atoms diffuse in A atoms. So, diffusion of A in A. Here so far we have been looking at diffusion of B in A. Here I am saying diffusion of A atoms in the structure of A. So, what do? We use a similar setup to measure that, except that instead of B atoms, I would put an isotope. I will I will produce a thin film, plated on the end of it, an isotope of A would be plated, and this isotope of A would be tracked and measured. What is the concentration of the A isotope at different distances after an experiment has been done for a specific temperature and time. With that, one can then obtain what is called as the self-diffusion coefficient. With this I will stop here and we will continue in the next lecture.